So we've seen from the last video that working out the multiplication by hand is a very tedious process, and it's much better left to a computer to do it for us. So if you go into the resources section, you'll find an Excel spreadsheet. So if you head in there and open it up, and make sure you're on the Tools tab, and you'll have a few options in front of you here. So if you click on the option here that says Floating Point Multiplier, then it'll open up a multiplier that I've created in Excel VBA. So let's have a little look at this and we'll see how this is all working. So the best thing to do is for you to go ahead and open it up and have a little play with it. Now it's quite intuitive and quite obvious once you start using it. We've got two numbers that we can put in. We can put in a value for x and a value for y, and those get into this box and this box. So let's just put something in quickly to get started. If we put a value of 5 in here, you see that the 32-bit floating point number changed. Now this here is a 32-bit floating number for the value of decimal 5. Now let's say we want to multiply it by a value of 7. So we put 7 in here. This is the y value. The y value, again, it comes up here at the top, and this is the 32-bit floating point binary representation of the number 7. And you'll see that the multiplication is done for us automatically. So 5 times 7 is 35, and you'll see that we've got the 32-bit floating point number for that multiplication. We've also got 3 bits at the end which we've used for rounding, but we'll talk about these later on. You'll also note as well that we've got the number type that we're interested in. So 5 and 7 and 35 are all normal numbers, so we've got normal numbers here. Now there's a reason for doing that, and it's that whenever we start introducing subnormal numbers, then we have to be careful about how we do the multiplication, but we'll get into that in a later video. So the value of 5 here as well, the value is equivalent to this binary representation, and we put the binary representation also in hexadecimal. Now this is a hexadecimal here, so this hexadecimal here is the same as the 32-bit. It's just a bit easier to write it in hexadecimal rather than writing 32 bits out all the time. You have an 8-bit method of writing out this. So for example, the first value of the hexadecimal is 0, so that's equivalent to the first 4 bits, so it's 0, 0, 0, 0. And the last bit here is a value of 4, and that's equivalent to the last 4 bits here. So the last 4 bits are 0, 0, 1 and 0, which is 1, 2, 4, so that's a value of 4. Now we did the same for the output as well. We've got the output in hexadecimal. So have a little play with this. You'll see that if you put in the negative values, you get the correct negative values as well. And if you can put the numbers in terms of exponents, you could write in 1e to the minus 20, and you can copy and paste, and you can see that it works it out instantly as soon as you've put the new value in. So you can copy and paste that in there, and you can see that in this instance here we've got 1e to the minus 20 times 1e to the minus 20, and the answer is actually going to be a subnormal. So we can see here it tells you we're multiplying a normal with a normal and getting a subnormal, and you can see it's a subnormal result because the exponent value is all zeros, but there's a value in the mantissa. So let's go ahead and we'll put our numbers in, and we'll see the multiplication done here, and we'll also see the multiplication in the background in the multiplication tree which I've built in Excel VBA. So let's put our two numbers in. We had our minus 0.7, and you can see it's changed these values here to the 32-bit representation, and we multiplied that by 492.75, and you can see here in the background, I'll actually put that back in. We put in 492.75, and you see the numbers rippling through. So it's worked out the actual value, and that's the actual value here, and this is the value in the 32-bit floating point representation. And again, you can compare that to the values that we worked out in the previous video. And we can also look at it in terms of the hexadecimal values. We're multiplying this hexadecimal with this one, and we're getting this value here. So let's go ahead and don't press clear, just press close, and we'll see what we have in this page here. So let me zoom in a little bit just so we can see it a little bit better. Now what we have here is the same representation that we had in the previous video, the one that we did by hand, but we've automated it here. So you can see here that we have the Y value as the top value, and we have 23 bits of the Y value. I can just get them in here. So we've got the 23 bits here of the Y value, and that's from this point here to this point. And we have the 23 bits. Now this is the 23 mantissa bits that we're multiplying. So we have the 23 mantissa bits for the X value here as well. And you can see that we've appended it with the value of 1. So this is the hidden 24th bit that we talked about. So we've added the value 1 on here, and we've added the value 1 on here. So we're actually multiplying together these two 24-bit numbers, and we get at the very bottom the multiplication of those, which is the 48-bit number. So that all the way along there is a 48-bit number. And what I've done is I've just highlighted the values of the 1 just to see the changes that map through whenever you change the value of the decimal input. So we have our 48-bit number here, and you'll note that I've put the first 2 bits in red because these are the first 2 bits that are going to be left of the decimal point. So in effect the decimal point is going to be at this point here. Now let's have a look and we'll see how we generated the exponent value. Now we started off with a value for our xe, so this is one of our exponents, and that's a value of 126. We then take away the bias of 127, and that's going to give us a value of -1. Now we do the same for the y component here, so we've got a value of 135 for the exponent of the y value, and we take away the 128, and we're given left with a value of 8. We add these together, and this is going to give us a value of 7. So finally what we do is we add back on the value of 127, and it gives us the value of 134. But this isn't us finished yet with the exponent. We still have one other thing to take care of. Now we mentioned before that this point here is the full point, the full stop, or the decimal. But this number isn't normalised. It's only going to be normalised when the last value is a value of 1. So it means that the full stop is going to have to move 1 position to the left to this point here in order to normalise the result. But if we were to move this 1 position to the left, then it means that the exponent is going to have to be added on by a value of 1. So this is equivalent to us going from our 2 to the power of 7 to 2 to the power of 8. So we have to add 1 onto this, and this will give us our final exponent value of 135, and this is the exponent value here in our binary format. So let's go ahead and we'll open up the tool and we'll have a look at another example. So I've ran it up again, but let's have a look at another example here. So let's say we're interested in 5 times 5, but whenever I put these values in, we need to keep an eye on the top 2 bits here. So let me put 5 and 5, and you can see that the top 2 bits go to a 0 and a 1. So whenever there's a 1 here, it means that we are already have a normalised answer, therefore we don't need to shift the decimal point. So we've got a value of 0 here being added on to the exponent. So if I put in the value of 50 times 50, you'll see here now we've got a 1 and a 0. So now we've got a 1 and a 0. We have to move the decimal point 1 place to the left in order to normalise it, and we add on our value of 1 here to the exponent. So let's look then at 500 times 500. Now in this case here we've got 1 and a 1. So in this case we still have to move the decimal point because the highest value here has to have a value of 1. So if we move the decimal point again one position to the left, then we are normalizing this result, and we have to add on that value onto the exponent. So you can see here that we're interested in the value of this most significant bit, because this is going to tell us whether we have to add on an extra value to the exponent or not. Now it also tells us whether we have to shift the mantissa. So let's say, for example, this one up here, you can see the actual result is going to be 11101, but you can see that the full stop is this point here. So now the full stop has moved one position to the left, and it's this point here. So it means that everything to the right of this point will be the new mantissa. So in effect, by moving this point up to the left, we're shifting the mantissa into the correct position. So everything we're going to be doing now with the multiplication tool is all about shifting the mantissa to the correct position, and that position will be dependent on whether we have to normalize the value or not. So let's go ahead and we'll summarize what we've learned here. So let's summarize what we've learned so far. If we look at the mantissa value for x, then we can say that it's going to be greater than equal to 1 and less than equal to a value of beta. Now beta here is our radix, so it's the base 2. So we're really saying that this is greater than equal to 1 and less than a value of 2. So I'll go ahead and I'll show you exactly where that comes from, just so that you understand exactly where we are with this. So I've opened up the tool that we've been using, and if we head into binary to decimal annotated, you can see that we've got the conversion tool here from binary to decimal. So if I just put in a few values here for the exponent to start off with, you'll see here that we've got the 1 plus 0 times 2 to the power of the exponent, which is just the exponent value here. But we're really interested in what is inside the brackets here, because what's inside the brackets here is a value of 1. But if I was to add on the mantissa goes up to 0.5, so this is now 1.5, and we can continue adding values on, and you'll see that this tends towards the value of 1, therefore this whole thing here will tend towards the value of 2, but it will never ever reach the value of 2. The closest it will get to is this 1.999, so on and so forth. So it'll actually be off of the value of 2 by 2 to the minus 23. So this is why we say that the value of m is going to be greater than or equal to 1, but it's going to be less than the value of 2. So now we know where that comes from. We have the same thing for the y value. Now when we multiply both together, we're going to have the mx times my. Well, we'll multiply the left hand side as 1 times 1 is 1. We multiply the right hand side is going to be beta squared, and it's going to be less than, but not less than or equal to. So we have our beta value here, as I said, as a value of 2. So it means that the mantissa here is going to be a value greater than equal to 1 and less than a value of 4. So really what we're saying here is that if you think about the two most significant bits, we're going to have actually two significant bits after the decimal point, because this value here is going to be a value of a number just less than 4. So in order to represent the value of a number just less than 4, we're going to have 2 bits. So the 2 bits are the bits 47 and bits 48 of the multiplication. So we can see then that the 0, 0 cannot occur, because we have to have a value that's greater than 1, equal to 1, less than a value of 4. So 0, 0 is not a possibility. But we can have a value of 0, 1, 1, 0 and 1, 1. And we've seen that whenever we were going through the multiplication, and you could see multiplying 5 times 5 or 5 times 50 or 500 times 500, and you could see the top 2 significant bits changing. So we've seen that the values that are generated for the significant bits 47 and 48 are going to determine whether we have to add an extra value on to get the correct exponent and also shift the mantissa. So we can see here that if this value is a value of 1, the 48th bit is a value of 1, then we're going to have to add 1 on to the exponent value, and we're also going to have to shift the mantissa 1 decimal point to the left. And if the most significant bit here is a value of 0, then we don't need to add the extra bit on to the exponent, and we don't have to shift the mantissa value. So this is the little table that we'll see cropping up with the other options that we're going to have whenever we look at subnormal numbers. But let's move on and we'll just finish this off. We can see the exponent was generated by the value of our exponent EX minus the bias. Then we added on the value of EY and we took the bias off again, minus the bias. And then finally, when we've added both of them together, we added the bias back on. And then we added the value of 0 or 1 onto it. So finally we can write this here. If we take the plus and the minus, this one cancels with that one. We're just going to be left with one of the 127s. So we can say the exponent is going to be given by EX plus EY minus 127 plus the value of 0 or 1, which is determined by the most significant bit. And also the mantissa is going to be a left shift of either a value of 0, that is no shift at all, or a value of 1. And also, just to note before we finish, when I talk about a left shift, I'm talking about the decimal point shifting to the left, as opposed to the entire mantissa shifting to the right. So that's all there is for this video. I do encourage you to go ahead and open up the tool and have a little play with it. Now just before we go, you have to note that we've only worked with normal numbers times normal numbers giving normal results. But it's a little bit more complicated than that, and we'll see that in the next video. So thank you for listening. I'll get you on the next video. Goodbye.